So, we are discussing slit designs. The optimum slit widths in any spectrophotometer you take, they are approximately between 0.2 to 0.7 millimeter. Basically, what is a slit? A slit is a simple material a metal plate in which a hole is made, that is a slit. I take a metal plate and make a small hole through which the radiation is coming. So, I put take the radiation source on the left side and then put a metal plate so that nothing comes out, and all the radiation that is coming out will be only through the slit. And the slit designs are normally in the form of triangles. So, optimum slit widths are 0.2 to 0.7 millimeters. Even though variable slits are also employed, there what we do is we take two metal plates like this and then make them increase or decrease the width in between, that is a variable slit width. So, the choice of a slit is a trade off between intensity and resolution. If I choose a very small slit, the intensity of the radiation coming out will be much less. If I choose a bigger one, then monochromaticity will be lost. So, it is always a compromise. So, the band pass, we define what is known as band pass width of a slit function as delta lambda, that is the amount of radiation corresponding to different wavelengths is given by twice width, twice the slit width and reciprocal linear dispersion of the monochromator. So, this is a very simple physics formula, and the effect of slit width what you can see is somewhere here, and here the peak things are normally you can see the sharpness of the peaks as the bandwidth varies from 3.4 nanometer, slit width is 1 nanometer, this is 0.5 and this is 0.1 millimeter. So, here bandwidth is more, 0.34 bandwidth is much less, and here it is 1.7 and it is 3.4 nanometers. Okay. So, you can see the peak heights are entirely different for the same system. So, we also need mirrors and number of mirrors and lenses in spectrophotometric optical arrangements, and they basically are used for collimating and focusing the electromagnetic radiation. Collimating means to get the wavelengths to get the radiation parallel, and focusing means we have to place the choose the place where the mirrors are kept so that the image of the radiation is sharp, and lenses are preferably avoided because normally lenses, as our knowledge of physics tells us that there will be normally chromatic aberrations associated with lenses. So, normally reflection losses occur up to 4% at each glass to air interface. So, thin metallic films are coated on glass surfaces, etc. They can limit the reflectance losses to 0.2%. So, these are all technical details, but what is important is when you buy a spectrophotometer, all these things you have to look into the technical specifications so that you get the optimum of the optimum instrumentation for the amount of money what you are spending to purchase a spectrophotometer. So, prisms, apart from lenses and monochromators, glass filters, we use prisms, and prisms we have discussed earlier. Fused silica or quartz prisms are required. Silica prisms are required for the visible range, and quartz prisms are useful for the ultraviolet range. The resolving power of a prism is given by this standard formula, and both Littrow and Czerney mounting are employed in UV visible spectrophotometers, preferably the former. That means 2 half prisms are not preferred, single half prism with a coated mirror surface on the back side. Now, the prisms, there is an arrangement, typical arrangement I am showing you now. Here is the slit, and from the slit I get a parallel radiation. Here it is a collimating mirror, and from the mirror the radiation is reflected back to a prism, either it may be Littrow or Cornu mounting, and the whatever radiation comes out should be a monochromatic radiation useful for measurement. So, when a 60 degree prism is employed, I need a bigger space, and then there is a requirement of sharper dielectric constant material. So, next thing is gratings. Gratings are better than prisms to choose the correct wavelengths. Almost all gratings are used in UV visible spectrophotometry are of reflection type. That means, the gratings are coated from the bottom, so that the radiation that is falling simply gets reflected, and the grating sizes varies from 10 to 25 centimeter. The quality of a grating depends on the straightness, parallelism and equidistance. What is a grating? A grating is a simple mirrored glass, okay, as I am showing you in this figure, with a number of grooves like this, and the number of grooves varies from 1200 to 30,000 grooves. So, basically whenever the radiation falls, you see that it is as if a number of prisms are employed in choosing the wavelength. So, this is the optics of the grating, and here there is a grating normal, and then the incident radiation is falling like this, it gets it goes out like this, and then it gets diffracted on the other side. So, this is the reflection, this is diffraction. So, the distance between the grating is known as grating spacing. So, angle of incidence need not be actually from the normal, but it can be through the different angle. So, what happens is, as the radiation falls on different rulings, there is constructive and destructive interference, and again we get a simple monochromatic radiation. This is the optics of the grating. So, modern ruled gratings present an inclined groove profile. That means, the gratings are not perpendicularly drawn, but they are drawn at an angle. Okay. So, these can concentrate most of the energy into a single order. This angle is called as the blaze angle. If it is drawn perpendicularly vertically, then it is a normal grating, but if I hold the pen in a slanting position and draw a number of rulings, then it is a blazed holographic grating, the efficiency depends on the wavelength where the angle of diffraction equals the angle of specular reflection. So, blazed gratings can concentrate most of the incident energy into a single order. The band pass width of a diffraction grating is limited by the groove density lines per mm. As I have told you, it varies between 1800 to 30,000, and then it also depends upon the focal length and the slit width what we normally employ. So, a grating of about 1200 grooves per mm and 25 mm mount, that is the size of the grating, with 1 mm slit offers a band pass width of plus or minus 2 nanometers. That is excellent monochromaticity as far as spectrophotometry is concerned. So, two collimated beams of a monochromatic laser beams can also be used to produce interference fringes on a photosensitive material deposited on optically true glass. This glass may be plane or concave. The portion of the photoresist exposed to the laser beams where they constructively interfere is then washed away. What I am trying to do here is I am trying to teach you how to make a grating. So, what I want to do is I take a metal plate, like this and then draw the rulings with a diamond cutter, or I take a glass plate, draw a ruling with a diamond cutter which are parallel with a machine. And for your information, I have to tell you that the first grating done in 1770 or something like that contained 30,000 gratings per centimeter. That means 30,000 prisms were made on the grating at that time itself. Nowadays, gratings are made made in a factory where the ruling is automated and the grating is coated with an epoxy and then done at a blazed angle, etc. So, holographic gratings are also done on reflective layer. Okay. You might have seen stamps which will look different colors if you look at it from different angles. That is a holographic grating. In your day to day life, holographic gratings are used on cars, car headlights and car stamps, 3D designs, and all these things are use holographic gratings, and holographic gratings can be produced up to 6,000 lines per mm and in sizes of 600 to 400 mm, that is 60 to 40 centimeters. Holographic grating carved on a concave surface when illuminated through an entrance slit creates an rotation, a near perfect image on a fixed exit slit. So, whenever you need a grating, you need an entrance slit as well as an exit slit. So, the blazed holographic gratings give a uniform throughput over the entire UV range. That is the beauty of holographic grating, blazed holographic grating. They give a uniform output over the entire UV visible range. So, the band pass of 0.4 to 4 nanometers over the entire UV visible range is obtainable. So, what I have told you so far is I want you to concentrate now. The radiation that is normally coming from a radiation source like tungsten lamp or something, that has to pass through a slit and then a monochromator, a lens or something to make the lines parallel. The parallel lines are passed through the prisms or gratings to get desired wavelength, and after the desired wavelength again we need an exit slit which is again triangular in nature, and once that come through the exit slit, what we get is the monochromatic radiation. That is the optics part of the spectrophotometer. Okay. Now, in this optics part, the arrangement of the exit slit and entrance slit is very important, and that is known as mounting. So, a mounting combination consists of an entrance slit, a mirror and an exit, a grating or a prism or something, and then again a transmitted light, reflected light, and that reflected light has to be collected back on the exit slit. So, the combination of entrance, exit slit and collimating mirror and the grating, that is called as mounting. So, these are all things which are normally not disturbed by a spectrophotometer user. It is all put it in a box and sealed, so that we do not disturb the thing. Also there is certain amount of problem with dust and other things. So the biggest enemies of spectrophotometric accurate measurements are the dust particles. So the whole optics part must be housed in a box where there is no entrance of the dust, which is not always possible, and quite often we have to open them and clean them, etc. That is a different science. A service engineer will take care of that. Now I want to tell you about some of the mountings. So as I told you, mountings are the different arrangements, and here I am showing you Ebert mounting. Here what is happening? An entrance radiation comes from the slit, falls on a collimating mirror, the reflected light is collected on a grating or a prism, and then again it is collected on the same prism, and once it comes out, the exit slit will be organized like this. So this the both entrance slit and exit slit are placed at the focal length of the collimating mirror. Okay. Now I will show you another arrangement where the mirrors, there are two mirrors instead of one mirror. Here you can see there are two mirrors. So entrance slit is here, it goes here, collects on the grating, again goes to another mirror, not on the same mirror like earlier, but comes out on the exit slit. So going back to the Ebert mounting, what we have here is the using a single mirror and double mirror. That is the difference between the two sets what I have shown you. The advantage of a single mirror is reflection losses are well compensated. Earlier I had told you that there will be about 4% error in the reflected losses, and then entrance and exit slits are on the same side. That means the instrument will become more compact, and this permits high aperture in a relatively small package. That means instrument becomes smarter, and a sine bar drive produces a direct readout of the wavelength on a linear scale. Suppose what is the wavelength coming out is depends upon how I rotate this grating. Okay. This grating is rotated using a hand operation or automatic operation. So the sine bar drive produces a direct readout of the wavelength. I can, if I am rotating mechanically, I can attach a wavelength scale as well. Okay, that is how the wavelength scale is made, and it is a linear scale. So cosine bar drive provides a wave number scale, that is inverse of that. So this is known as another arrangement known as Czerney-Turner mounting. Two concave mirrors are usually used. Here it has a low aperture f6 to f10, but it offers better stray radiation and resolution characteristics. Stray radiation should be minimum and resolution should be optimum. So this is known as Czerney-Turner. 99% of the spectrophotometers nowadays being produced in the market nowadays are based on Czerney-Turner mountings. So another arrangement is, this is Littrow, single entrance slit and exit slit. The difference is entrance slit is coming from the top, and exit radiation is also coming through the same slit, but slightly at a lower level. So this is known as Littrow grating mounting. So there are the advantage of this is high grating efficiency, good spectral purity, small aberrations, and much more compact than double slits. Very simple arrangement. So the grating equation, basically is m lambda is equal to 2d sin theta or b into sin I plus sin r, where b is the distance between the adjacent grooves and I is the angle. This I have similar figure I have already shown you, but what is important in this case, in this figure, is here you will see the radiations wavelengths 300, 500, 700, 900. This is known as the first order wavelength. Any first order wavelength will also have half of that wavelength as second order. This is known as 0 order, this is first order, this is second order, third order, like that. So, in any grating, these are the basic problems with gratings. We have to minimize the second order and third order gratings, because that is the wavelength that also comes out automatically along with any chosen wavelength. So, for example, if you choose 1100, it is always associated with 550 nanometer and half of that is again 366 nanometers, and similarly 900 will be having 450 and 300, and it need not be in the same exactly half, but it will be approximately. So, this is the problem with gratings. So, there are a lot of work has been done in reducing the higher order radiations coming from a grating, so that the wavelength accuracy is optimum. So, actually if you are measuring around 1100, you will not be measuring 550 in general, but it will serve as a stray radiation which will help, which will result in a slight aberration. I assume the same thing is true with 360. Similarly, if you go for 900, it is always associated with 450 and 300 nanometers, 700 with 350, 233, like that. It is a very simple calculation. You can actually calculate the first order, second order, third order wavelengths using the simple formulas. So, here is a small practical problem. If I have a grating of 1180 grooves per millimeter, diffracting at a normal incidence, that means I is equal to angle of incidence is 0. So, it diffracts a 300 nanometer radiation. I can simply calculate what is the sin r, m lambda by h minus sin I. So, this will be 0, sin angle of incidence is 0. So, sin I is 0. So, m lambda by h is what I get here, converted into centimeters, and then 1 into 3 into 10 raised to 5 divided by that is the convert everything into centimeter. What comes out is 0.354, and this corresponds to 20.8 degrees exit angle. So, the second order of this would be 150 and third order would be 75, they appear at the same angle of 20.8 degrees. So, some amount of filtering is necessary if you want to prevent the overlap of the higher orders in a grating, that is important. Okay. Now, how do I produce a grating? A grating is produced using a master grating. Once every time it is not possible to get the same quality of grating by taking a machine and doing it. So, what we do normally is we take a master grating, make a master grating and then produce the replicas. So, basically it is a slow, arduous and time consuming, but once a master grating becomes available, replica gratings can be made very easily, and that too at low cost. So, replica gratings can be made by applying a film of a parting agent. That means, I take a grating, master grating, I take a master grating, put a little bit of oil or butter or something, which can be taken off, and then over that I put epoxy. The epoxy will harden, producing a replica of the grating on the epoxy. Okay. On this epoxy is mounted on a aluminum plate. So, when you take it out, I have the grating ready. So, that is the whole idea. So, glass or quartz base I need to take, and to the aluminum layer with epoxy cement. After an appropriate time interval, the replica can be separated. This is a very simple, easy way of producing a grating, which is a very high quality engineering material. So, this grating, coming back to the Echelle gratings, an Echelle grating you must know about it, because lot of people, sales people, etc., when you want to buy an equipment, they come and say, sir, ours is an Echelle grating. It is not a blazed holographic grating, or it is not a simple plain grating, but it is an Echelle grating. So, what is an Echelle grating? So, an Echelle grating is blazed in such a way that it has relatively broader surfaces, that means very few lines, reflection lines. So, reflection occurs and the reflected radiation is concentrated in the preferred direction. So, in UV visible monochromators, the grating usually have about 300 or fewer grooves, maybe 75 grooves, 100 grooves, like that, instead of 1200, 1800 grooves in a normal blazed holographic gratings for spectrophotometer. So, for such gratings, angle of reflection and angle of incidence are same, fixed. So, we get n lambda is equal to 2d sin beta, that is whatever we are fixing the blazing angle, and then what happens is this the difference is like this. This is a normal grating normal, the angle of incidence is fixed and angle of this thing is reflection is also fixed like this. This is the distance between the two. So, the reflection losses in from this case are very less, because it is not very near. Instead of 1800 grooves like this, we have only 75 or 80 grooves. So, the reciprocal linear dispersion is given by this formula, and light gathering power is better, where f is the focal length, and the linear dispersion is of an Slit is very large. It also contains several orders of wavelengths which overlap, and a comparison of the conventional and an Echelle monochromator is given here. One conventional is 0.5, this is 0.5, 1200, this becomes 1700 mm, this is 10 degrees, this is 63 degrees, that is the diffraction angle. Order is 1 and here it is 75, and resolution is 62,400, whereas it is here in this case it is 763,000. So, reciprocal in accuracy, what you can see here is the accuracy. So, it must be remembered that even though most of the monochromator systems do deliver fairly narrow bands of electromagnetic radiation, large number of mirrors and lenses are still required in any spectrophotometer. So, if you happen to know by any open by any chance a spectrophotometer, do not be baffled if you see a number of small mirrors and lenses. Okay. So, that completes our discussion on the optics part. Now, we will concentrate on the absorption cells. In the next class. So, please remember that what we have discussed is the instrumentation of a spectrophotometer. We have discovered only half of it. Now, we will be discussing about the absorption cells as well as the detection and measurement of the spectrophotometric cells, and then we will discuss about the typical commercial instruments in the next class.